Today, I would like to discuss the design of the small signal dynamic behavior of the active antenna. We have already studied um, the configuration of the controller last time. I want to pick it up from there. So there's a little bit, let's say, again, the same thing as we did it last time, but now, let's say, more just quick and with some hand calculations. And then we will focus on frequency compensation techniques. And there will all frequency compensation techniques that are listed in the book will also be demonstrated in the design of the active antenna. But let's start with a recap of the design of the small signal behavior of the active antenna. So we were aiming to make the active antenna with a two-stage controller, and a circuit that I started with was a circuit with a CS stage at the input and a complementary CS stage output. But unfortunately, that controller was a non-inverting one, so we would have positive feedback instead of negative feedback. And we solved in this example this problem by adding an inverting current amplifier, unity gain current amplifier in the loop, which is also known to you as a current mirror. Today, I will stick to this concept, so no implementation of the current mirror, because we want to study the frequency compensation techniques and don't make want to make the things more complicated than only to focus on the frequency compensation techniques and the way to implement them. Of course, if there will be a current mirror, or if you are designing the amplifier with a differential stages input, which was your homework, you could uh, you have to adjust the frequency compensation, but the techniques as they will be introduced today are exactly the same. So that's why we want to focus on the techniques and don't make the stuff more complicated than necessary. So this is the small signal diagram um, of the circuit. Um, if we use the first stage as a CS stage, which is shorted, and the drain gate capacitance is solely included in the input capacitance. So there's no connection between the drain and the gate in a small signal diagram. That is often justified, definitely in the case of a shorted stage, because then the Miller effect is not present. And secondly, the gate drain capacitance is much smaller usually than the input capacitance. So you see the first stage, GM1, and the effect of the current mirror is just that I flipped the sign of the controlled current source. Now it is like an non-inverting stage instead of an inverting stage. So basically, the first stage, the CS stage, including the current mirror, is shown in this controlled source GM1. Then GM2 is the complementary parallel connection. You can the two transconductances, the two voltage controlled current sources of the two transistors are in parallel. Their input capacitances are in parallel, so you can make one simple model from that. And also there I ignored, for the sake of simplicity, and I will explain later why this is justified, the presence of the feedback capacitance, just included it only in the input capacitance. Well, let's focus on that maybe immediately, because we have to go back to the discussion of the CS stage and the dynamic behavior of the CS stage a few lectures ago. There we have seen that if the feedback capacitance is CGD is much smaller than the input capacitance, then and there is also a capacitive load, which is definitely the case here because we have CF in parallel with CISS, which is again in parallel with CSF, sorry, in series with a parallel connection of CS and CISS1. That is the capacitive load at this second transistor. So if the feedback capacitor is smaller than both the input and the load capacitance, then it does not Of course, it cannot introduce a new pole because it would be a loop of capacitors, but also its influence on the product of the poles is negligible. Only it affects the sum of the poles, which means that is described by the Miller effect, which means that if I would now evaluate the poles and zeros of this circuit and compare it with the result, for example, obtained from SLICAP, in which those capacitors are present, then I would find a different result for the sum of the poles, but not for the product of the poles. That's the idea. And for the bandwidth design of the amplifier, the product of the poles is decisive, and the sum of the poles more has to do with the stability. Of course, both poles should be part of the dominant group of poles if they want to contribute to the bandwidth. That can always be checked at a later stage. So let's do this. You can make a loop gain expression by selecting either GM1 or GM2 as loop gain reference, and you find something like this. There's 2RC, which is the load. RC stands for the characteristic resistance of the cable. So the two RCs in parallel is the load, and the gain in the whole stage is GM1 times GM2. And then there is a capacitive divider from the output to the input, and that's the factor that you find in the numerator, CF divided by the sum of all the capacitors. And then, of course, we have the poles. We have a pole in the origin caused by CISS2. So you simply find S times CISS2 in the denominator. And there is a pole formed by two RC in parallel with a series connection of CF and the parallel connection of CS and CISS. And that is this expression. So this is how I write down such an expression. I'm not going to network theory and do all these substitutions and write 5 pages. I just do it in this simple and short way. Now, for the bandwidth estimation, we need to have the product of the loop gain and the poles, the so-called loop gain poles product. So the only thing I need to do is remove the 1 and the s's from this expression, and then I have the loop gain poles product, and then you can simplify this expression as is shown here. So it's nice to see that the resistance RC, the characteristic resistance of the cable, is not part of the loop gain poles product. Of course, assuming that both poles are dominant. You see, and also the feedback capacitance is not part of the loop gain pole product. That is nice of doing such an expression symbolically. It immediately tells you something about the circuit. You cannot change the bandwidth of the circuit by changing CF, or you cannot change the bandwidth of the circuit by changing RC. It will just be given by these parameters, GM1, GM2, and the both input capacitances and the source capacitance. So I did something in between the last presentation and this one. That is, I optimized the noise and the drive capability a little bit, and this gave me another input capacitance. Let's say maybe you remember that the input capacitance should be equal to the antenna capacitance to have the lowest corner frequency of the 1/f noise. And in my previous simulation with SLICAP, maybe you remember, but you can see it on the video, it turns out that this corner frequency was about 30 kilohertz. But 100 kilohertz would be good enough. So I can basically make CISS smaller. That means I can make a smaller transistor and operate also at another inversion coefficient. I optimized this and came to a CISS of 1 PF. Later on, we will see that this is very beneficial for frequency compensation. So there is some interaction between the two, of course, but this is what we will discuss later. And the second transistor was about 1.2 PF. It's the two transistors in parallel. They were quite large because they needed to drive the load. If we put this all in numbers, we have a bandwidth, an achievable bandwidth of 1.5 gigahertz. That is what we expect. So if I would run, including everything, the more complete model with SlideCap, then I would expect a bandwidth in the order of 1.5 gigahertz. You see, I rounded all my numbers a little bit, and there were only the most dominant effects are included here. The first pole is in the origin, formed by the current source GM1 and CISS2. You see there, for DC, there will be an infinite voltage across CISS2 if there is a finite current caused by GM1. So this is a pole in the origin. And the second pole was 2RC, so the RCs in parallel, in series, sorry, and that in parallel with a series connection of CF, and a parallel connection of CS and CISS. And this is it in the what you read in the expression. That's the 4 pi comes from 2RC and 2 pi. So if you calculate that, you will come up to 450 megahertz, and you will see that SlideCap gives a little bit more. It gives more than 1 gigahertz for the second pole. And that is because of this pole splitting in the second stage. I did not include the feedback capacitance there. I just included it in CISS2, but I didn't include it in the feedback. So the Miller effect basically splits the pole, but for the bandwidth, I do not expect any effect as long as the second pole is still dominant. Well, in this case, it is dominant at 450 megahertz, and we will see in SlideCap it is also still dominant because it's a little bit more than 1 gigahertz, and the bandwidth is 1.5 gigahertz. So the bandwidth, it can be designed, and we can say we need only 30 megahertz, that this is adequate. This is good enough. So let's go to dual stage.py and verify these numbers with SlideCap. It's a little bit different from the last time because I optimized the values for the width. So I created a file here, a master file, like I did it also with the MATLAB versions, by making all kind of. Oh, I think I should make it a little bit larger for the resolution. So, see, I'm just importing other Python files, and by importing them, well, the statements in these files will be executed. So it's another way of typing execute. So it's like just import the thing and it will be executed, and I create the complete HTML file. And you see only init project is in the first one, because that creates the new main index page. So if you go to what I want to run now, dual stage Phantom 01. No, that's not what I want to run, because that's already the Phantom 0, and I promised you to run the just normal dual stage. So if I want to run the dual stage, that is this file. And it's the same as we did last time. I just defined the antenna 5 PF and the feedback capacitance 2.5 PF. The current of the the quiescent current of the output stage, and the rest is defined in the circuit, and we are going to plot the whole asymptotic gain model. That is basically what I'm going to do. So I will run this file, and then we will see in the window here the results. And there you recognize the plots of the asymptotic gain and the loop gain that is infinite because of the pole and the origin. So the DC loop gain infinite, the gain and the servo function a little bit peaking because of the complex poles. But the interesting point is the crossing where the black line, the loop gain line, crosses the 0 dB, and that is just above 1 gigahertz. And we can better go to the HTML file to read the results. That is much more simple. So let's go to the HTML file and do the index and show them in this window. Dual stage, that's what I just run. And here you have again, this is the circuit. You see the width is a little bit adjusted. We have 400 micrometers instead of 1.2 millimeter. And this is instead of 1.25 micrometer, it is only 300 nano. So the input capacitance is much smaller. And the first stage is still running on 1.5 milliamp. And this was optimized for that the noise is still okay, and with a little bit less capacitance. So here you see the output transistor with the quiescent current of 1 milli. And I added, let's say you can enter for U2, this is the output transistor. You can add a current for the N device and for the P device. So the N device, I gave the quiescent current plus a sink current, an extra sink current. And the P device, I gave the quiescent current plus an extra source current. That means that later on, I can change the current of one of the two devices, simulating as if it is sinking or sourcing current from or to the load, and then see what the pole and the pole zero pattern will do, and if the thing will be stable for under all conditions. I did not yet include such simulations, but it can be done in this way. So let's go to the, I don't show you the numbers because you just believe me that they are okay. You can download all this. And you see the nice thing here is I predicted 1.5 gigahertz and it says 1.42 gigahertz. So the prediction is not at all bad. It's close to the result, and the Q is 1.4. So the poles, there is a little bit of overshoot as we have seen in the Bode plot, and compensation may be required to have no overshoot. But look at the loop gain. In the gain you see two poles, but also in the loop gain, two poles and two zeros. The loop gain has two positive zeros, which means that they increase the phase shift for higher frequency, and they increase also the amplitude. So for the phase, they act as if it are poles. And they're not that far away from the dominant group. You see, the bandwidth of my amplifier turns out to be 1.5 gigahertz, but this is at 22 gigahertz, and this one at 30 gigahertz. So the effect, maybe it is, let's say, since it's more than a factor 10 away, but there are two of them. So the effect cannot be ignored. And we will see later on that if I calculate the compensation, the frequency compensation for the case in which there are no zeros, there's only two poles, that I will be a little bit off with the result. We need to correct it a little bit because of the effect of the pole of the phase shift caused by the zeros. But for now, we're not yet talking about compensation. We were just checking the bandwidth, and you see that our hand calculation that you can really do with a simple circuit closely matches the result. And that is what the message of this presentation. Maybe again the Bode plots, but now a little bit larger. So here you see this 1.4 gigahertz is where about the peaking happens. In the blue line is the gain. The black line is the loop gain. It crosses the 0 dB axis there where you have this peaking, where you have the bandwidth. The loop gain reference is correctly chosen because you see the asymptotic gain is frequency independent and minus 6 dB. That is exactly what we expect for the ideal gain. So that is basically, sorry, for this small signal behavior that we already did last time, but now we did it with some new values, and we showed how to do it with a simple hand calculation.